All right, so today we continue with the topic of orthogonal projections. Okay, so just to remind you, we have defined them as follows. So definition, given V an inner product space and T a linear operator on V, assume that T is a projection, okay, in the usual sense of being a projection. So let me recall, this means that there exist two subspaces, W1, W2, subspaces of V, such that V can be written as a direct sum of the two. Okay, so V can be written as W1, direct sum with W2. Okay, and for any X vector in V, since this is the direct sum, it can be written, X can be written as the sum of two vectors X1 plus X2 with Xi in the corresponding subspace Wi. We have that the value of T of X is just X1, okay? So in this case, we say that T is a projection, and now a projection is said to be orthogonal. So then T is an orthogonal projection okay, if moreover we have these two conditions about orthogonality of the range and the null space. So we have the range of T. If we look at its orthogonal complement, we get the null space, and symmetrically we have that the orthogonal complement of the null space of T is equal to the range of T. Okay, so this is what it means for a projection to be orthogonal, an orthogonal projection. And we finished with two remarks last time that I want to recall. So remark one, if the dimension of the space V is finite, okay, then either of these two conditions implies the other one. Okay, where by these two conditions, I mean that the orthogonal complement of the range is the null space, and vice versa, the orthogonal complement of the null space is the range of T. Okay, so in the finite dimensional case, to check that our projection is orthogonal, it's enough to check either of these two conditions, okay, because then the other one automatically follows. But we started discussing an example which shows that this is not true if the dimension of our inner product space is infinite. Okay, and the example for this was the following. So we define the inner product space V to be L2, little L2. So this consists of vectors which are given by infinite sequences. So AI, INN, infinite sequences. So AI of real numbers, which is square summable. So such that the sum over AI square, I from, 1 to infinity is finite. So it converges, okay? The sum of squares in the sequence converges. So our vectors are all such sequences of real numbers. And then it is a real inner product space with the following operations. Okay, so this is where we finished last time. So we have to define the sum of two vectors. Okay, so the sum of a sequence given by AI and the sequence given by BI, INN, is going to be the sequence where the ith entry is the sum of the ith entries of these two sequences. Okay, so we have this for all sequences AI, BI in L2. And we also have to say what multiplication by scalar corresponds to. Again, we do this coordinate-wise. So C times the sequence is given by the sequence where the entry in the position I corresponds to C times AI for I in N, okay? And so this we have for all C scalars in R, okay? And finally, we have to say what the inner product is. So the inner product of two sequences, AI and BI. So the inner product of two sequences is given by the same formula as the dot product. So we take the sum over all AI times BI for I from 1 to infinity. And the point is that then this is going to be a real number. The sum is going to converge. The series consisting of the products. This follows because each AI and BI was square summable. Okay, so just follows by standard properties of convergence for infinite series. So finally, we have that the dimension of V is infinity. To see this, you can think about the vector of the form 0, 0, 0, 0 everywhere except the position I, where we put 1, and we have zeros everywhere else. Okay, so it's an infinite sequence with 1 in the position I. You can check that all of these are going to be linearly independent. Okay, so this gives the standard basis by the analogy of the space R to the N. So this is the infinite dimensional variant of it. Okay, so you can verify that this would give us a basis. Okay, so the dimension is infinite. Now, the point of considering this example is to show that the two conditions of orthogonality are in fact separate. So it's not like one implies the other in this case. So we consider the subspace W, which is going to consist of all sequences AI, which are square summable. So we're going to look at all vectors in L2, okay? For which there exists some J, an index J, such that the corresponding coordinate AI is equal to 0 for all I greater than J. Okay. So we restrict, we consider the subspace consisting of all sequences, which are eventually 0. Okay, so it's an infinite sequence, but from some point on, you only have zeros in it. So of course, note that every such sequence is going to be an element of L2, right? Because if there are only finitely many entries, then of course the sum of squares is a finite number. So it is convergence sequence, square convergence sequence, yeah? Okay, so this is indeed a subspace. And then we have the following properties of this subspace. So I'm not going to check them in detail. I encourage you to check this yourself. So to get used to this interesting infinite dimensional space. So the orthogonal complement of this subspace is going to be 0. Okay, so we leave it as an exercise. But the hint why the orthogonal complement is going to be trivial is because you should use that W, the subspace W, is what is called dense in the whole space V. So what does it mean to be dense in a space? So this means that for every epsilon, a positive real number, for every X in V, there exists some Y in W, so that the distance between X and Y is going to be smaller than epsilon. Okay, so density means that every element of the whole space is arbitrarily close to some element of the subspace, right? So like no matter what small distance I fix, epsilon, I can always find some element of the subspace W, which is within this distance epsilon of this given point of the whole space V. Okay, that's why I refer to it as density. Somehow you can find points of W everywhere in V. in any small neighborhood. Okay, so using this, you can deduce that the orthogonal complement is 0. Now we can look at the double orthogonal complement. So this is going to be the orthogonal complement of the trivial subspace by 1. And this is the whole space V. Okay. But note that W is not equal to V. So W is a proper subspace of V. Okay, so how to see this? We need to exhibit an element of V, which is not in W. Okay, so to see this, consider, for example, the sequence given by 1 over 2i. So the ith entry is 1 over 2i. This sequence is square convergent. You can check it, so you have to remember some of the basic convergence tests, yeah, for infinite series. So this is in V, because it is convergent, like I said. So the sum over 1 over 2 to the power I, or I from 1 to infinity is finite. But the sequence is not in W. Okay, so it's not an element of the subspace W, because of course 1 over 2i is not equal to 0 for all I, right? So it never starts, it never becomes 0 from any point onwards, because each entry is actually positive, right? 1 over 2i, it gets smaller and smaller and smaller, but it stays positive. So this is not an element of W. So the conclusion we get here is that W is not equal to W perp perp. Okay. So we see that the orthogonal complement of the orthogonal complement of W is not equal to W itself. So this illustrates that the argument we used in the finite dimensional case to show that each of the conditions implies the other one doesn't work here. Okay, so this was just to give you one example. We won't really discuss infinite dimensional spaces much in this course, but this is one of the most important ones, infinite dimensional inner product spaces. Okay, all right. So now let's try to understand further the difference between orthogonal projections and regular projections and some of their properties. Okay, so assume we're in a situation that W is a subspace of V and the dimension of W is finite. Okay, but we are not making any assumption on the dimension of V itself, could be infinite. So then by theorem 6.6, we know that every element Y of the space V can be written as the sum Y equals U plus Z for a unique choice of U in W and Z in the orthogonal complement of W, right? So a vector can be split into the sum of an element of the subspace and the one in the orthogonal complement. Okay, then we can define the map T from V to V by taking T of Y equals to U. Okay, so now from the definition above, we see that then T is an orthogonal projection on the subspace W, right? Because again, U is the component corresponding to the component which is in W. Yeah, so this is a projection on W. Yeah, okay. However, it's not unique. Well, sorry, in this case, it is unique. So there exists exactly one orthogonal projection on W, even though there might be many different ones, like we remarked last time. For orthogonal projection, there is exactly one. Okay, so moreover, there exists exactly one orthogonal projection on W. Okay, because if, well, let's show that there is only one. So assume T and U are two orthogonal projections. On W. Then from the definition, we have that the range of T is equal to W is equal to the range of U, right? Hence, we must have that the null space of T is equal to the orthogonal complement of the range of T, because we are assuming that it is an orthogonal projection, right? Which in turn is equal to the orthogonal complement of the range of U is equal to the null space of U. Okay? So from this, we see that then for any Y in V, we have that Y can be written as U plus Z for unique U belonging to the range of T, which is the same as the range of U, and unique Z belonging to the null space of T, which is the same as the null space of U. Okay, but by definition of projection, we then must have that T of Y is equal to U, and which is also equal to U of Y, right? So this shows that T and U must agree. And Y was an arbitrary vector, right? So T is equal to U. So this shows that there can be only one orthogonal projection to a given subspace. Okay. And finally, definition. So to stress this, because now we know uniqueness, we will call T with this property the orthogonal projection of V on W. Okay, so again, there might be multiple different projections onto the same subspace along different subspaces, but orthogonal projection is unique. Once you specify on which subspace you're projecting, the orthogonal projection onto it is unique. Okay, just to give you some visual example of this difference. So the difference between projection on W versus the orthogonal projection on W. Okay, so as usual, let's consider like one of the simplest examples that we like, R square, and take W to be the subspace given by the span of the vector 1, 1. Okay, so let's draw this. So I have the coordinate axes, X and Y, and we have the subspace W given by some line through the origin, right, which corresponds to the point 1, 1. Okay, so this is the line of the span of this vector. Okay, now let U T be as in the picture. So U and T are going to be two projections onto this subspace, which I just draw visually without specifying the formula. Okay, so assume V is a vector. For example, this is V, some vector in my space. Then I can consider two projections. First, I can take this to be U of V. Okay, so this is going to be obtained by just taking the line like this. And alternatively, we can define the map T, which is determined by the orthogonality. So if this is going to be T of V, where I have that the angle of this projection is orthogonal, okay, straight angle. Okay, so we have these two projections. Then T is the orthogonal projection. But U is a different projection. Okay, and visually the difference is determined by the orthogonality of the resulting component. Okay, so note again that V minus T of V belongs to the orthogonal complement of W. So this is the line W, I should have noted. Okay, on the other hand, V minus U of V does not belong to the orthogonal complement, right? Because the angle here is not straight. So it's not in the orthogonal complement, the difference between V and U of V then. Okay. So this is just an illustration in R2. All right. So now let's go back to precise results. And we have a theorem which gives us an algebraic description of orthogonal projections. Okay. So remember, for the usual projections, we know that they're characterized by saying that T is equal to T squared. Okay, so recall T is a projection if and only if T is equal to T squared. So we would like now to strengthen this to obtain an algebraic characterization of when a projection is orthogonal. So we need some additional property, right? Because as we just discussed, not all projections are orthogonal. So that this condition is provided by the next theorem. This is theorem 624. So assume that V is an inner product space and T is a linear operator on V. And in this result, we are not actually assuming that V is finite dimensional even. We can do it without the finite dimensionality assumption, okay? So assume this. Then we have the following equivalent. So T is an orthogonal projection on some subspace W if and only if T has an adjoint T star, okay? And we have that T squared is equal to T. So this is the part which we already know from just being a projection, but also it's equal to T star. Okay, so moreover, T is self-adjoint. So if we require this additionally, we get orthogonal projections from just arbitrary projections. All right. Note now here that I'm saying T has an adjoint. So remember, we know that if the space is finite dimensional, then every linear operator has an adjoint. But here, since we are not assuming finite dimensionality, existence of the adjoint must also be demonstrated, yeah, because some linear operators in infinite dimensional spaces don't have adjoints. Okay, so proof. So we need to prove two implications. So first, let's show left implies right. Okay, so suppose that T is an orthogonal projection okay, then we immediately already know that T squared is equal to T because T is in particular a projection. Okay, then to prove the right-hand side, we only need to show that the adjoint T star exists and that it's equal to T, so that T is self-adjoint. Okay, so by definition, we have that V can be written as the direct sum of the range of T and the null space of T. Okay. And we also know that the orthogonal complement of the range is equal to the null space. Okay. So this we know by, since this is an orthogonal projection, we're assuming. Let's see, there's a question in the chat. Does T necessarily have an adjoint? So that was exactly what I commented earlier. We are not assuming that the space is finite dimensional. It always has an adjoint. Every linear operator has an adjoint on a finite dimensional space. So we are not assuming that the dimension of V is less than infinity. Okay. So on infinite dimensional spaces, some operators don't have adjoints. So we will check it additionally here. Okay. So by definition, we have that V can be written as the direct sum like this. So now let X, Y be two vectors in V. Then we can write them as X equal to X1 plus X2 and Y equals Y1 plus Y2 for some vectors X1, Y1 in the range of T and some X2, Y2 in the null space of T, right? So here we're just using that this is the direct sum. So then every vector can be written like this, okay? But then we have the following for the inner products. So we look at X inner product with T of Y, okay? Now just substitute X by X1 plus X2, okay? And T of Y is, so T is the projection on, so right? So then the result of T of Y is going to be just Y1. Because Y1 is the component which is in the range of T and they are orthogonal, yeah? So we have Y1. Now by the property, by linearity of the inner product, we can just open it as X1, Y1 plus the inner product of X1, Y, excuse me, X2, Y1, right? We have X2, Y1, yeah, okay. But now look, this is actually 0, right? So this is 0 because Y1 belongs to the range of T, X2 belongs to the null space of T, and this is the orthogonal complement of the range, right? So then this has to be 0 because they are orthogonal. And so we are left with X1 inner product with Y1, okay? And we also have similarly that T of X, Y, if you look at the inner product of these two, we get that this is equal to the inner product of X1, right? And Y1 plus Y2. Now, again, this can be opened as X1 inner product Y1 plus X1 inner product Y2. So this is going to be 0 again, because, well, by the same reasoning, right? So they have to be orthogonal since they come from the range and the null space. And so we are left with simply X1 inner product Y1. Okay, so we obtain the same thing on the right. So it means that the things on the left are also equal, right? So we conclude that the inner product of T of X with Y is equal to the inner product of X with T of Y. And this holds for all X, Y, and V, right? Because we started with arbitrary vectors, X, Y, and V. And so we have that T star exists and equal to T, right? Because this formula shows that T satisfies the definition of the T star, right? Because here, normally we would have T star of Y, but now T satisfies this formula. And remember, the adjoint of a linear operator is a linear operator which satisfies this formula for all X, Y. So this just tells us that T is T star. Okay. All right, so this shows the implication from left to right. So next, our task is to show the converse implication. So suppose that T square is equal to T is equal to T star. Okay. Then we know that from the first equality, T square equals to T, we know that T is a projection. Okay, but we must additionally show that it is an orthogonal projection. So we must show that the range of T is equal to the orthogonal complement of the null space of T, and vice versa. The orthogonal complement of the range of T is equal to the null space of T. Okay, so we have to check these two conditions, which is exactly the definition of when a projection is orthogonal. All right, so let's try to check it. So fix two vectors, x in the range and y in the null space. Okay. Then we have that x is equal to T of x is equal to T star of x. So this is just our assumption, right? Here. Well, we're using all of this, that it is a projection and that T is equal to T star. Okay, so we have this. So now let's calculate the inner product of x and y. So we want to show that x and y are orthogonal, right? Because we took x from the range and y from the null space. So in order to do this, we have to determine the inner product equals to 0. Okay, so just substitute now using this equality. Substitute T star of x inner product with y, right? Now this in turn is equal to x inner product with T of y, right? Because we have, yeah. And so this is equal to x inner product with 0, right? Because remember, y is in the null space. So T of y is equal to 0. So we get the inner product of x with 0, which is of course then 0, right? So we have demonstrated that x belongs to the null space of T orthogonal complement, right? Because y was an arbitrary element of the null space, and we have shown that x is orthogonal to it. So the conclusion of this part is that the range of T is contained in the orthogonal complement of the null space of T. Well, let me see a question in the chat. How did we go from xy to T star xy? From xy to T star xy. Okay, so this question is about this equality. So this we did by looking at this, right? So x is equal to T star of x. This is part of the assumption that T is equal to T star and T is a projection, right? Okay, so we have this inclusion. Range is contained in the orthogonal complement of the null space. But this is not enough, so we have to show the converse inclusion as well, right? Because we're trying to show the equality. Okay. So now let y be an arbitrary element of the null space of T, orthogonal complement. And we want to show that then this belongs to the range as well. Okay. So take y like this. Then we have, let's look at the norm of y minus T of y. Okay. And let's look at the square, so we don't have to take square roots when we work with the inner products. So by definition, this is just the inner product of y minus T of y with itself, right? So y minus T of y. It's just the definition of norm. Now this, we can use linearity of the inner product. So this is the same as y inner product with y minus t of y minus t of y inner product with y minus t of y. Okay, so I just use linearity for the first coordinate. Okay, but then we have that t applied to y minus t of y. Okay, so consider this. This is the same as t of y minus t square of y. Okay, but by assumption, t square is equal to t, right? So we get that this is the same as t of y minus t of y. So it is 0. So we have that y minus t of y belongs to the null space of t, right? Because if we apply t to it, we got 0. So this means that the argument, this vector, is an element of the null space. Okay, so this belongs to the null space. Hence, we get that the inner product of y with y minus t of y is equal to 0. Right? Because remember, we took y an element of the orthogonal complement of the null space. All right, so we get that this is equal to 0. And also, we have another calculation, so we can look at t star of y minus t of y. Okay, so what do we get here? Well, basically the same thing, right? So we have t star of y minus t star t of y. So here I'm just using linearity of the adjoint, right? But by the assumption, this is the same as t star of y minus t star of y, right? Because we're assuming that, remember, we are working, what is our global assumption? That t square equals t star, right? So using this, we get down to this, but this is again 0. Yeah. Okay, so this is 0 as well. And so we conclude that the inner product of t of y with y minus t of y is going to be y inner product with t star y minus t of y. So this is just the definition of the joint operator. Okay. But by what we just observed, this is going to be y inner product with 0. Okay, this is from here. Okay, so we get, and this is again 0, hence, yeah. Okay, so we have obtained two things at this point. Look, we have obtained that this inner, we have obtained, sorry. So we are looking again at the square of the norm of the difference of y minus ty, right? So it consists of these two vectors, two scalars, this and this. And we just proved for each of them that they are 0 for each of them separately, right? Okay. So combining, we get that the square of the norm of the difference, y minus ty, is 0, which can only happen if y is equal to t of y, right? But t of y is, of course, an element of the range of t, right? So we got that y belongs to the range of t. Okay, so the conclusion is that the orthogonal complement of the null space of t is contained in the range of t. Because remember, y was any arbitrary vector of the orthogonal complement of the null space. Okay, and on the previous page, we have the opposite conclusion, right? So we know the range is contained in it, and the orthogonal complement of the null space is contained in the range. So combining, again, we get that the range of t is equal to the orthogonal complement of the null space of t. Okay, so we get one of the two conditions that we are trying to show. Okay, so what remains is to observe that the range of T orthogonal complement is equal to the null space of T orthogonal complement, and this contains n of T. So this holds by a homework exercise. Okay, so we just need to show the equality. There remains to show the equality, where equality amounts to showing the opposite inclusion. So what's missing at this point is this inclusion. Okay, so let's try to check it. So take a vector in the set on the left. So suppose X belongs to the orthogonal complement of the range. Okay, then for any vector Y in V, we have that the inner product of Tx with Y is the same as the inner product of X with T star of Y. This is just, again, the definition of the adjoint. But this is equal to X inner product with T of Y, because T is equal to T star by assumption, right? So we get this. But X inner product with T of Y is going to be 0, right? So we know they are orthogonal. X is an element of the orthogonal complement of the range, and Ty is in the range. Okay, so this is 0. So we also must have T of X is equal to 0, right? Because here Y was any vector, and we have shown that the inner product of T of X with any vector is 0. This is only possible when T of X itself is 0. So we conclude that X belongs to the null space of T. Okay, but that's exactly what we wanted, right? So this gives us this inclusion. So the total conclusion is then again that the range space of T, if we look at the orthogonal complement, this is the same as the null space of T. Okay, so that's it. This gives us both implications of the theorem. There was a bunch of calculations here, yeah. So yeah. I hope you could follow. If not, makes sense, I think, to review yourself to make sure that every step makes sense. I mean, I tried to say on each step what we are using. So hopefully you could follow. If it was too fast, feel free to ask questions. Yeah, I'll pause for a minute. Yeah, so we checked these two parts of the calculation, like let's say this is first part and this is second part, they correspond to showing that this and this, the two summands giving us the norm, the square of the norm, above 0. Yeah. Okay. Okay, any other questions about this proof? Okay, if not, let me just make a couple of remarks about all of this. So remark part 1. So something about the matrices first, yeah? So assume that V is an inner product space of finite dimension, okay? And assume that W is a subspace of V. Okay, so given this situation, now assume that T is the orthogonal projection of V on W. Okay, so let's look at the orthogonal projection here. Now assume that V1, V2, etc., through Vk, let this be an orthonormal basis for the subspace W. Okay, so an orthonormal basis for W. We know we can extend it to an orthonormal basis for the whole space. Okay, so extend it to an orthonormal basis, which we can write as V1 through Vk. So this is the ones we already had, and we have to add some. So Vk plus 1 through Vn extended to an orthonormal basis for V. So we know this is always possible. This was theorem 6.7, right? That, given an orthonormal basis for a subspace, we can extend it to an orthonormal basis for the whole space. Okay. Then we can look at the matrix representing T with respect to beta. Then this matrix is going to be of the special form. So it's going to be of the following form. It consists of blocks. So we have Ik, and then we have 0, 1, 0, 2, 0, 3, with 0, 1, 0, 2, 0, 3, all zero matrices of appropriate sizes. Okay, so the sizes have to be whatever is left, because we know that this is k by k. Yeah, corresponding to this, to the block. And then we have to fill everything else with zeros. All right. So we see that this is the case for an orthogonal projection onto a subspace. The matrix has this particularly simple form if we choose the basis properly. If we choose a basis starting with an orthonormal basis for the subspace W, and then complete it to an orthonormal basis for the whole space. So to see this, just remember the definition, right? So we are forgetting the coordinates, which correspond to the we're forgetting the coordinates of. So we take a vector x. To calculate T of x, you have to write x as the sum of x plus the orthogonal complement. Right, so you take the component which is in W and the part which is in the orthogonal complement to W. But for that but then the corresponding coordinates, you're going to get that they're 0, right? Because the image of T of x is just the part which is in W. So that's how we see that the matrix has to have this special form. Okay, and we will use it soon. And part 2 of the remark, if U is any projection on W, we may choose a basis gamma for V such that the matrix representing U with respect to gamma has the same form as above, but this basis gamma that we can choose like this is not necessarily going to be orthonormal. Okay. So the strength of the orthogonal projection is that we can always represent matrix in this particularly simple form. And I'll stop here today, but next time we'll begin discussing we'll discuss the spectral theorem, which tells us how it's actually possible to decompose a linear operator into orthogonal projections. Yeah. So we'll see that this special kind of linear operators, orthogonal projections, they in fact quite general and help us to analyze arbitrary linear operators. So, but this will be next time. So I'll stop here today. Thank you all for your attention, and yeah, I'll see you next time. Okay. Yeah. Thanks everyone.